Good morning, everyone. I'm delighted to welcome you to today's presentation. My name is Dr. S.K. Singh, and I hold a PhD in this fascinating field. Today, we'll be exploring gas chromatography, mass spectrometry, or GC, MS for short. Over the next few minutes, I'll guide you through what GC, MS is, how it works, and its important applications. I'm excited to share this knowledge with you, so let's get started. Let's start with the basics of GC, MS, which is a powerful analytical technique that combines two main components. First, we have gas chromatography, or GC, which is responsible for separating the different compounds in a mixture. Then, there's mass spectrometry, or MS, which is used for identifying and quantifying those compounds once they've been separated. This combination makes GC, MS incredibly versatile and widely used across various fields. For example, in pharmaceuticals, it helps analyze drug compounds and ensure quality control. In forensic science, it's essential for detecting and identifying substances in criminal investigations. Environmental analysis also benefits greatly, as it allows us to detect pollutants and trace chemicals in the environment. One key advantage of GC, MS is its suitability for volatile and semi-volatile compounds. These are substances that easily vaporize, making them ideal candidates for analysis with this technique. Overall, GC, MS provides detailed, reliable information that helps us understand complex mixtures in many scientific and industrial applications. Now, let's talk about the principle of gas chromatography. The core idea here is that separation is based on two main factors: volatility and how each component interacts with the stationary phase. When we introduce a sample, it's first vaporized so it becomes a gas, and then it's carried through the system by an inert gas like helium or nitrogen. As the components travel through the column, they don't all move at the same speed. Instead, they elute at different retention times, which helps us distinguish them. The basic principle involves a two-step process. First, gas chromatography separates the mixture into its individual components. Then, we use mass spectrometry to identify those components based on their mass-to-charge ratio, or M. This combination gives us a powerful analytical tool. It offers high sensitivity, meaning we can detect even trace amounts, and it also provides structural information about the molecules, helping us understand what they are. So, in essence, gas chromatography is about separating components based on their physical interactions, and then identifying them precisely, making it a fundamental technique in analytical chemistry. Let's take a closer look at some sample injection principles. When introducing samples into the chromatograph, we typically use techniques like split injection and splitless injection. Split injection involves dividing the sample so only a portion enters the column, which is useful for analyzing high-concentration samples. On the other hand, splitless injection allows the entire sample to go into the column, ideal for trace analysis. Now, the samples themselves need to meet certain criteria. They should be volatile, meaning they vaporize easily, and thermally stable so they won't decompose at high temperatures. For compounds that aren't naturally volatile, we often use derivatization to modify them and make them suitable for analysis. Moving on to the basic principle, the core concept here is the separation process within the column. We're primarily using capillary columns, which are made of fused silica and coated with a stationary phase. This stationary phase is key because it interacts with the analytes and helps separate them based on their affinity to the phase versus the mobile phase. Separation efficiency is influenced by several factors. The length and diameter of the column play significant roles. Longer columns generally improve resolution, while the diameter affects the flow and separation speed. Temperature programming is also crucial. By gradually increasing the temperature, we can optimize the separation of compounds with different volatility profiles. Finally, because capillary columns are highly efficient, they provide high resolution, allowing us to distinguish closely related compounds more effectively. This combination of column design and temperature control is what enables us to achieve precise and high-quality separations in our analyses. On slide 5, we're diving into the ionization principle, which is fundamental to understanding how gas chromatography mass spectrometry works. A common technique here is electron ionization, or EI. In this process, high-energy electrons are used to ionize the analyte molecules. Essentially, these electrons collide with the molecules, knocking electrons off and creating positively charged ions. This ionization process is crucial because it allows us to detect and analyze the compounds based on these ions. What makes EI particularly valuable is that it produces fragment ions. These fragments give us important structural information about the molecule, helping us identify and characterize the compounds in our sample. Now, connecting this to the overall theme, the basic principle revolves around how we transfer these ions into the mass spectrometer for analysis. This is where the interface comes into play, specifically in GC-MS coupling. Because we're dealing with a gaseous mobile phase, we can directly couple the gas chromatograph to the mass spectrometer without complex conversion steps. The transfer line is designed to keep the analytes in a vapor state, which is essential for accurate analysis. And because of this gaseous transfer, the interface remains relatively simple compared to liquid chromatography mass spectrometry, or LC-MS systems. So, in summary, the ionization process, especially EI, is central to generating informative ions, and the interface ensures a smooth, efficient transfer of these ions from the gas phase into the mass spectrometer for analysis. Now, let's take a closer look at the mass analyzer principle. Essentially, this component is responsible for separating ions based on their mass-to-charge ratio, which is often abbreviated as M. This separation is crucial because it allows us to identify and quantify different ions within a sample. There are several common types of analyzers used in mass spectrometry. The first one is the quadrupole, which uses oscillating electric fields to filter ions of specific MZ values. Next, we have the ion trap, which can trap ions temporarily and then selectively eject them for detection. Then there's the time of flight, or TOF, analyzer, which measures how long it takes ions to travel a set distance, giving us precise MZ data. It's important to note that the choice of analyzer impacts both the sensitivity and the resolution of the instrument. Sensitivity tells us how well the system can detect low-abundance ions, while resolution indicates how distinctly different ions can be separated. Understanding these factors helps us optimize the instrument for different analytical needs, which ties back to our overall goal of accurate, reliable analysis in mass spectrometry. Let's dive into the quantification principle. Essentially, it's based on comparing peak area to concentration, which is a fundamental concept in analytical chemistry. This approach allows us to quantify how much of a substance is present by measuring the size of the peak in our chromatogram. We use calibration curves and internal standards to improve accuracy and reliability. Calibration curves are created by analyzing known concentrations, and then we compare our sample peaks to these standards. Internal standards help account for any variations in the analysis process, ensuring our results are consistent. This principle is especially useful for trace-level analysis, meaning it can detect substances at very low concentrations, like parts per million or even parts per billion. That's crucial in fields like environmental monitoring or forensic analysis, where detecting tiny amounts matters. When it comes to detection and data output, the detector records ion intensity over time. From this data, we generate a chromatogram, which plots retention time against intensity, and a mass spectrum, which shows MZ ratio versus intensity. These outputs are powerful because they enable us to identify compounds by comparing the spectral patterns to known spectral libraries. This identification process is essential for confirming the presence of specific substances in complex mixtures. Overall, this quantification approach ties together the measurement, detection, and identification steps, providing a comprehensive way to analyze and understand the composition of our samples. Now, let's talk about system suitability and compliance, which are critical for ensuring our analytical methods are reliable and meet regulatory standards. First, under system suitability tests, we focus on key parameters like resolution, repeatability, and sensitivity. These tests help us confirm that our instrument and method are performing consistently and accurately before we proceed with sample analysis. Moving on to compliance requirements, there are several important aspects to keep in mind. For instance, 21 CFR Part 11 sets the standards for electronic records and signatures, ensuring data integrity and security. Audit trails are essential for tracking all changes and actions within the system, providing transparency and accountability. SOP-based operation emphasizes the importance of following standard operating procedures to maintain consistency and quality. Method validation, guided by ICHQ2, is another cornerstone, covering key parameters such as specificity, linearity, accuracy, precision, and the limits of detection and quantification, LOD and LOQ. These parameters demonstrate that our method is fit for purpose and capable of producing valid, reproducible results. Finally, robustness is about ensuring that our method remains reliable under varied conditions. All these elements, system suitability, compliance, validation parameters, are required for regulatory submissions, illustrating that our analytical approach is both scientifically sound and compliant with industry standards. This foundation supports the integrity and acceptance of our data in regulatory reviews. Now, let's talk about some of the key advantages of this analytical technique. First, it offers high sensitivity and selectivity, meaning it can detect even very small amounts of compounds with great precision. This is especially important when we're working with complex samples or trace levels. It's also excellent for analyzing volatile compounds, which tend to evaporate easily, making this method particularly useful for flavor, fragrance, or environmental testing. Another major benefit is the availability of strong spectral libraries, which significantly aid in the identification process. These libraries enable us to compare our data against a vast database, making identification faster and more accurate. Finally, this technique is widely accepted in regulatory testing environments. That means it's trusted by authorities and organizations around the world, ensuring that our results meet strict standards and are compliant with regulations. Overall, these advantages make this method a powerful, reliable choice for many analytical applications, aligning perfectly with our goal of achieving precise and trustworthy results. For further support, please feel free to reach out to us. We're here to help with any questions or additional information you might need. Don't hesitate to contact us. We value your engagement and want to ensure you have all the resources necessary to succeed. Thank you so much for your time and attention today. We appreciate your participation and look forward to supporting you in your journey.